Good afternoon. My name is Ilesomi Adeshida. Everybody calls me Ade, so don't be shy to call me that. I'm the Dean of the College of Engineering at the University of Illinois, and it's my great pleasure, actually, to welcome you here this evening or this afternoon. It looks great outside. To what we call the Engineering at Illinois Dean's Distinguished Lecture, Leadership Lecture. I'm sure all of us know this university has been created since 1867, and I think the College of Engineering since essentially 1870. So there's a long tradition of both standing and international and national reputation of leadership, impact, and collaboration. Engineering at Illinois, that's how we brand ourselves, the College of Engineering, is committed to the intellectual and societal development of future generations. We have a lot of students here today to demonstrate that. This lecture series that we started a few years ago brings eminent leaders and foremost experts to the campus to share knowledge and facilitate discussions among students, faculty, alumni, and the community at large on important challenges impacting the global society. Today, we address one of the most important challenges impacting our global society, that of climate crisis and energy, and we welcome one of the world's most innovative leaders and Engineering at Illinois alumnus, Dr. KR Sridhar, the principal co-founder and CEO of Bloom Energy and the creator of the Bloom Box. You'll find out more about the Bloom Box later. Prior to founding Bloom Energy, KR, as we all popularly know him, was director of the Space Technologies Laboratory at the University of Arizona, where he was also a professor of aerospace and mechanical engineering. Under his leadership, the Space Technologies Laboratory conducted research and development for Mars exploration and flight experiments to Mars. As an advisor to NASA, he's worked for the NASA Mars program to convert Martian atmospheric gases to oxygen for propulsion and life support. Was recognized by Fortune magazine, where he was cited as one of the top 5 futurists inventing tomorrow today. As one of the early pioneers of green tech, Dr. Sridhar has served on many technical committees, panels, advisory boards, and has many publications to his credit, and patents also. Sridhar received his MS in nuclear engineering and PhD in nuclear engineering and PhD in mechanical engineering from our college, and his BS degree in mechanical engineering with honors from the University of Madras in India. KR believes that we can solve our current energy problems through a combination of technology, innovation, and conservation. He has pioneered new applications of solid oxide fuel cells and technical innovations founded upon creative thinking and new business models. We'll learn more about this today. It is my pleasure now to introduce Dr. KR Sridhar to tell us why the energy revolution will be the next big thing. Please welcome KR.
Good afternoon. Can you hear me? That's great. So, Dean Ade, thank you so much for introducing me and the kind words. It's a great honor to be here, to be talking to you all. It feels very nostalgic. I spent a lot of time here in Champaign-Urbana. It's a magical place. I'm sure as students you all recognize that. We'll get into energy and other things later, very shortly. But what makes this place magical is not the buildings, not the quad, not anything else. It's the camaraderie of the students, how each one of you can feed on each other, and the tremendous faculty who absolutely care to build you into great citizens. It's a standing room only, but there's one seat up here And, but I just want to say that that seat is actually occupied in spirit by somebody that I want to dedicate this to, Professor B.T. Chow. I see my master's advisor sitting out here, and thank you for being here, Professor Jones Stubbins, but this is my PhD advisor, and he would have very much wanted to be here. And I know this, and I'll tell you why. But talking about faculty, let me take 30 seconds to tell you something about a cliche that's used all the time, giants in the field. We hear that all the time. This man is not that cliche giant. He was a true giant. He built mechanical engineering. Most of us know that. Professor Stubbins was one of his early PhD students. I had the fortune to be his very last PhD student. And just a few months ago, I received a letter from him. I want to put this up for you. A man, 91 years old. I wish I had a handwriting like this. Okay? But that says something about the kind of faculty that this place has. Look at this. You wouldn't see anything scratched out, anything done. And Professor Jones will agree with me. What I think would have happened is the previous day, Professor Chow would have written this letter in draft, put it away. The next day, he would have modified it 2 times with different color pens. And then finally written the final draft, even though it's coming to a student for whom he doesn't have to do it. It was not who it was going to. He cared about when his name goes on something, there's a pride associated with your work. So what he taught me was not just engineering. What he taught his students, and this is what we get from faculty, we learn life lessons. He taught about what is needed, and I see people straining to read what's in there. So let me just put one thing up here, okay? So this one talks about another quality of Professor Chow. I was this lowly PhD student, but look at how he is addressing me. And he did that even when I was doing my PhD. He treated me and every other student as somebody that he can learn from, somebody who was a friend. It was not just the brain that shared wavelength, it was the heart that shared wavelength. It's pretty remarkable. And look at what he said. Here's why I know he's here in spirit. He said, health permitting, I'd like to nominate you for the Distinguished UofI MECI Alumnus Award. That's what I'm here to receive tonight, which is the occasion in which we were able to do this. So it is with mixed feelings that I wish that seat was occupied by him physically also, but I know that spiritually he's here. This is what you all have in every faculty that you have in this university, in this college. And as students, make the most of it. If there's one thing you're going to learn, nothing about energy, learn this and you will do really well in life. Okay, getting to the energy issue, right? What is the reality? There are more than 2 billion people that live without access to power. There's no electric line by where they are, and they can't afford it. That's 2 billion with a B, not a million with an M. The global population is growing. By 2050, we'll have 2 more billion people on the planet at a minimum. So 4 more billion people that need access to energy, access to electricity. The world is training to provide energy and electricity to the 3.5 billion people it is serving today. If you think we have an energy problem today, fast forward it and think about what is out there, what is coming, what we need to do. And then think about the fossil fuel, the fuels from under the ground. Okay? I equate that to a feeding bottle. We as human civilization were given this as a feeding bottle to just grow up. And we as engineers, technologists, scientists need to grow up and figure out how to now start using fuels that are not from the feeding bottle. And that will take time. It's not something that's going to happen overnight. This is a problem that we're going to be solving for decades to come because of the scale of the problem. Okay? And there's increasing energy prices. So I'm not going to depress you here from the time I start, right? Everything that I told you was a problem. Everything I told you was a crisis. A crisis is a terrible thing to waste. It's an opportunity. Okay? As an entrepreneur, as young people that are looking forward, you're going to say, thank God my previous generation was dumb enough to do what they did. In my lifetime, this crisis comes, which means in my lifetime, this opportunity comes. I have the greatest opportunity out here to do what I need to do. Okay? That's how I want you to think about something that faces humanity. Because in entrepreneurship, in how problems get solved in the world, there's always the Malthusian people that say we'll have to go back to the caveman and his kind of life. And Darwin always wins. People adapt to change. That's what happens. And that'll happen here. This is such a huge opportunity, a market opportunity, a social opportunity, something where you can do good and make good, that there's just no way we're not going to solve this problem. And guess what? All these other crises, and pick your crises, are going to help you solve the problem. Everybody is going to be rooting for you to find the solutions. Why is that? If you're worried about climate change and what's happening with global warming, that's just one crisis. But think about energy security. Think about 24/7 businesses, 24/7 healthcare, airports, IT centers, financial centers that cannot afford not to have power. Think about security from that perspective. Think about energy costs and where they will go if 4 more billion people want the same supply and there's a supply-demand mismatch. Think about what that inelasticity is going to do to prices. And population growth that I touched upon, and the expanding economies. Let's talk about this for a minute. And let me illustrate this with a very simple chart. What you have on the x-axis is energy consumption per person. What you have on the y-axis is how much money they make in a year. Okay? And you can see poverty is down below, affluence is up there. But it's something more important. Look at the scale. It's a log-log scale. You all understand what this means. If I had plotted it, it'll just shoot up. If people go simply from $100 to $300 per person per year, which is about $1 a day, if they go to 1,000, look at what that does to energy use. It goes up tenfold per person. Multiply that by the 4 billion people. Are we going to tell them that they cannot have the same kind of life that we want to have? Or are we going to provide them that kind of life and make them our consumers and increase their quality of life? I think we should do the latter. That's the energy problem framed in a nutshell. So we know the aging infrastructure. I joke that since Edison, there's not been a good idea in energy, right? That's really made an impact. But think about what's going on. We have very large power plants that are capital intensive, and they cannot scale down. You cannot bring economies of scale to smaller sizes. Because they're big, they're polluting, they're noisy, they're put hundreds of miles away from where you live, and then you put a transmission distribution grid and lose energy as you go. Everything is being improved. Each of these things are being improved. But these improvements here are evolutionary, and the energy demand is going on a completely different scale. So these two are not going to blend. And if we don't figure out a paradigm shift, we cannot capitalize on the opportunity, so to speak, or we can't solve the problem. So are there analogs out here that we can look at? Think about mainframe computers and then distributed computing. This campus knows all about that. This campus was in the forefront of both these technologies. And see what happened with distributed computing. Do you think that there will be software engineers in the developing world, in the numbers that we have, creating the kind of lifestyle for everybody, if the only way people had access to a computer was large mainframes connected by wires to dumb terminals? No. How would your life be if you didn't have distributed computing? Think about that. It radically shifted what you did. So you went from centralized to distributed. Take telephony is the next example. When we had copper wires with landline telephones, it's only us older folk that still, when we have a house, have a landline telephone. I bet all you young people never have gone to your apartment or dorm and ordered a landline telephone, correct? Look at what's happened. The world. Look at what's happened in the world. You can go anywhere in the world and see somebody walking with a cell phone. It is a capital light infrastructure that allowed them to go from centralized to distributed and provide access. And I'll talk more about that in a second. Why should the same paradigm of centralized to distributed not happen in energy? There is market proof that it changes lives. It changes paradigms. Okay? So let's take one more thing and then talk about energy. There's something between hard infrastructure and soft infrastructure. If you build a very large power plant, you can recoup the costs of it and provide the low-cost, affordable electricity only if it lasts 40 to 50 years. The average age of a power plant in the US, look at that, 46 years. Okay? You all know the pace at which engineering development happens, whether it's materials, whether it's electrical, whether it's infrastructure. Guess what? You can't retrofit that. When you build a power plant, it stays for that long. We need to go into a software infrastructure that can change as fast as technology changes to be able to catch up with what we need to do. That's a very powerful idea. Why is that important? Let's just look at this example. Okay? The landline telephone versus the cell phone. Between the time of Alexander Graham Bell and mid-1990s, landline telephones had penetrated 21 lines for every 100 people on the planet. 21 lines for every 100 people. That didn't mean 21 people had electric, like landlines. There were offices, there were multiple lines, but the total number was 21 out of 100. In 15 years, mobile phones penetrated 98 out of 100. Okay, those are the statistics worldwide. Look at what it did to cost. Now let me ask you a question. If replacing this with this was so expensive that for 40 years you couldn't change it after you got innovation, would that revolution have happened? Hard infrastructure versus soft infrastructure. A very important philosophical question that you need to ask yourself. Okay? You know the answer. It's a rhetorical question. So when I was working on Mars to make the planet Mars sustainable, I won't go into that in detail. I'm happy to answer that in questions. But my thinking when I became a faculty at Arizona going from Illinois was very simple. In space, we call ourselves space explorers, space exploration, but we really do space trekking because we are backpackers and not explorers in space. We don't hunt and gather. An explorer hunts and gathers. Okay? Lewis and Clark were explorers. That's not what we do in space. You need to learn to live off the land if you're a true explorer. And Earth is a cradle. It's not if, but when human spirit will explore and go to other places. So I was trying to figure out how to make the planet Mars sustainable. What kind of technologies do you need? How do you produce oxygen, fuel, electricity, heat? That's what I was working on. Between the Martians not paying me very good money and something else that I saw, I just figured out that I can take what I learned there and apply it to this opportunity that I talked to you that I saw about 10 years ago coming. So we started a company using the same technology, a solid oxide technology, and I'll talk a little bit about it. I understand it's a very diverse audience, so I'm not going to get too technical on any one topic, but inspire you to think differently about the energy field. And we got the company funded using VC funding. Again, some of you, young people may be interested, happy to talk to you during reception about that. And we wanted to create a product, a black box. Don't think about that as a Bloom box. I'm not trying to market this to you. I'm not selling you anything. But I'm going to use the Bloom example just to talk about how you can think about something differently. And that is not the solution to the energy problem. It is a solution to the energy problem. Each one of you hopefully will innovate in your own way and create other solutions. Okay. So what we did here was simply to create a fuel cell that is a ceramic substrate, that is the electrolyte, which conducts oxygen through vacancies in its crystal structure. So oxygen ions will go from a high concentration region to a low concentration region because it's a distorted fluoride structure. And like any electrochemical device, it will need an anode and a cathode, 2 electrodes. And when you apply a charge, oxygen can go through, or if you have a partial pressure difference, it can be driven by oxygen, and you can get electricity out. So it can operate both ways, as an electrolyzer or as a fuel cell, either taking electricity and converting that to chemical energy, or taking chemical energy and converting that to electricity. So to tie it to Mars, what I was doing on Mars was taking solar photovoltaic electricity and converting that to chemicals that humans need. What we're doing in Bloom is turning it around, taking the chemicals that we have and converting it directly to electricity without going through the in-between steps. What happens in a power plant, you all know, fuel and oxygen burn, it creates thermal energy, it raises steam, runs a turbine, so thermal energy becomes mechanical energy. There's copper coils around it, the mechanical energy is converted to electrical energy, right? So there are steps that happen. And what the thermodynamic police and tax collectors do is every time you go from one form of energy to another form of energy, they take some away from you, right? So it's a very inefficient process when you go from changing one form to another form. This is a direct energy conversion, so the Carnot efficiency laws don't apply to it. It goes from chemical energy directly to electrical energy. So that is a fuel cell. So something 10 centimeters by 10 centimeters, 4 inch by 4 inch, very thin wafer, about 150 microns in thickness, produces about 25 watts. That's the simple building block. On that building block then, you layer them together with flow fields, and you build something about the size of a bread loaf, and that's a 1 kilowatt fuel cell stack. You put multiples of those stacks together in a box the size of a large refrigerator, and that's about 25 kilowatts. 25 kilowatts will roughly do a Starbucks. Think about that. So put 4 of those together, very important, right? Especially in student life. Put 4 of these modules together, you end up with a box about the size of a parking space, and that will do 100 kilowatts, which will be a small supermarket, or 100 homes on average, small homes. Okay? Now, that is an energy server, and just like in a data center, you take compute servers and put them together. You can take these boxes and put them together to do half a megawatt, whatever size you want to do. So it's a very modular approach. Why is this modular approach important, and why did we take this approach? When you build something that's a single building block and repeat in high volume the very same thing, you can bring down cost. If you try to customize and build it every single time, you can't bring down cost. At the end of the day, the mission is affordable. Clean has to be a byproduct. The world does not pay for clean. The world pays for affordable, buys it for what they need, and by the way, it needs to be clean. Okay, so let's talk about clean. If we use natural gas compared to marginal US grid of what needs to get added, because of the high efficiencies, because of the lack of transmission distribution losses, we will do about 67% better in carbon footprint. If we use biogas, and many of our clients use that, what will happen is, on a net basis, because the carbon in the gas comes from the atmosphere and then goes back in, on a net basis, you're zero. So even using fuels, you can be either sufficiently green, significantly green, or totally green. So that's the clean aspect of what we do. Now, Now let's talk about reliability. What we do in reliability is very simple. Remember the 25 kilowatt refrigerator size boxes we talked about? There are 4 of them making up the 100 kilowatts. Each one is self-sufficient. Each one has a power converter on its own. So they're hot swappable. In a typical installation, a customer would do about half a megawatt. So there'll be 5 of these boxes. It is actually 20 independent power generators that are put together as a cluster. So if any one were to fail, you can hot swap it while everything else is working. So as a system, it is fault tolerant while anything may be subject to failure. And it takes us 2 hours to swap this out. Again, I said I'm not trying to talk about Bloom, I'm trying to give you some concepts. What's the concept out here? Murphy will be kind to everybody the same way. Murphy's law will apply. Anything that you design will fail. Anything you build will fail. Accept that in your initial thinking. And plan for that as you build and design something and say, especially new technology is prone to failure. What can I do to convince a customer they should still use this? Well, build in the modularity from day one. So it goes into the design thinking. So again, remember, when you try to design something, build something to change the world, you need to put yourself in the end user's shoes and ask, what is it that they will look for? Why is it that they will not adopt? What do you need to do to bring a new technology in? It's not just about an invention. And as a technologist, as somebody who had a lot to contribute to building this technology, I think I can say this, about 10 to 15% of a company's success is its technology. It's a necessary condition. It's definitely not a sufficient condition. Everything else is a lot of other things that need to come in. So the other thing we think that's going to be very important is time to power. Especially in our part of the world where we are all NIMBY, right? Not in my backyard. The legislation, the environmental impact reports and all that need to happen take a very long time to put a power plant together. People cannot wait that long. If you can, from the time that you go in, within a few hours, install a power plant for somebody and power that building, think about how powerful that is. So that became one of the requirements with which we wanted to distinguish ourselves when we built it. So things were built modularly. The reason they're built in single pieces is if you had built the whole thing together, you would need a crane to lift it, and you'll need a crane operator, and it'll cost a lot more money than a forklift operator. Okay? Think about what you need to be thinking about design when you're trying to put a product together. Anything new? So then, again, the modularity and the reliability, and think about what is happening in the world, right? Most businesses that need reliable power will purchase a diesel genset and buy that with their own money on their balance sheet and keep it idle for 99.9% of the time, just when the power fails. And the grid, which is the pay-as-you-go model, is what they will be paying and keeping this equipment idle. Is that capital efficient? You don't need to know economics to know that's not capital efficient, right? So we just flipped the model. We said we have to build a box which is always used by somebody and let the grid be the backup. So that's how we flipped the model, and it became very attractive to our customers. Fuels. It's my personal belief that you cannot democratize the world if you don't democratize fuel. As long as you do something that any one particular geography is going to have a lock on fuel, that's going to be a problem. So we wanted to make a box that can work on a multitude of fuel, almost agnostic to what the hydrocarbon is, as long as there's a carbon or a hydrogen or both. Okay? And we can work on these things, and I'll talk about how we can do this in a little bit. But the important thing is this box, you don't need to change the box. You don't need to say ahead of time what fuel you're going to run it on. On the fly, you can change the fuel, and the system is capable of adapting and working with that fuel. And that's very powerful. That makes sure that the markets are not going to play you. Okay? If you have a natural gas disaster somewhere in a pipeline, you can bring in propane and keep running. And that's going to be important in the world. And then how do you translate that to a customer? How do you take that concept and translate that to a customer? How do you sell them a vision and how do you do that? That's a very important part of building a business. I'll give you an example of when I sat with the CEO of Coca-Cola, what I did. I just used one chart. I didn't tell him about anything else. I said, don't worry about the box. I'm not going to explain this to you. But assume that you have this black box. Whether it is existing fuel like natural gas or just the orange peels from your orange juice that you need to dispose of, becoming a biogas, giving you electricity. How cool would that be for your sustainability goals? Right? But then later on, you can add these things. This box is going to generate enough heat so you can do water distillation and water purification. Even from that biogas, it's going to put out CO2. You can carbonate your drink with that. And whether it's a hydrogen truck or whether it's an electric truck, you can run this with that. Initially, you're signing up with me for this, but we can give you all this. Wouldn't you like a complete energy solution that is in your own hands? So translating that flexibility from thought process all the way to a customer becomes extremely important. The mission is a lot larger. We started Bloom to change the world. Okay. If you ask the employees in the company why they're there, that's what they're there for. They're missionaries. It's a phenomenal team. I'm just the mouthpiece representing them. Okay. It's a phenomenal team, and their mission is to change the world. What can you do in the middle of Africa? What can you do in any part of the developing world? You can go from biomass all the way to syngas, and then run the electricity to be able to get lighting and cooking and things like that. But then the heat can be used for water purification, refrigeration. The hydrogen that comes out or the electricity that comes out can become their transportation solution. So it becomes a complete energy server, which now does not require either a transmission distribution line, because you can have a microgrid in a little village of 100 people. And it does not require a fuel line, because it's the biomass around them that they can use locally to what they need to do. That flexibility, that pathway, is extremely important when we think about where the future 4 billion people that we talked about earlier would get their electricity from. Affordability becomes very important. So here again, I just want to give you a glimpse of the model, whether if you're an entrepreneur, if you're entrepreneurial in your engineering thinking, better develop a sense for the business side of it. That becomes extremely important. When we started the company initially, we used to sell what is called a capital purchase model. Our first boxes that we sold to Google and eBay and those people were all capital purchase. So they'll buy the box from us. They'll buy the fuel from a fuel provider. They'll get their own electricity. And there, what they care about is a 3 to 5 year payback period, which means whatever they paid for the capital of the box, including the cost of capital and everything put together, maintenance, all put together, pays off in 3 to 5 years. If you get a 3 year, you get a 24% internal rate of return. If you get 5 years, you get about 15% rate of return. That's a good return on investment for a capital purchase for a company. However, within a year of doing this and people buying, the financial crisis hit. Okay? Even companies that had huge sums of money did not want to take their gunpowder and spend it on things that were not essential to the business. They could just buy electricity from the grid and not do. So we had to innovate. What did we do? We created something called the Bloom Electrons program. And what we did there is we worked with bankers, and like investment bankers like Credit Suisse, and put together a model where the equipment was owned by a project company. It bought the gas, it bought the box, it took care of the technology, and simply signed up the customer to a 10-year contract that was half a cent to 1 cent lower than what they were paying the grid. They take no risk. So imagine walking up to a chief financial officer or a chief executive officer or an energy officer and say, I'm going to sell you a box cut that out. I'm not going to sell you a box. I'm just going to give you electricity the same way you get electricity. You're going to pay a bill at the end of every month. Okay? And you don't take any technology risk, and you only pay if you produce electricity. And by the way, it's going to be cheaper than what you're paying them. For 10 years, it's fixed. And you can go out and claim that you're environmentally friendly. What part of this would you not buy? Right? That's what we did, and we created something called the Bloom Electrons program. And one of the educational institutions that you're all familiar with, probably Caltech, is a very big customer of that. 1/3 of Caltech campus runs on Bloom. So all these customers signed up in a hurry. And what did we do? We're a very young company. What have we done so far? We have put enough power to power about 10,000 homes a year so far. It's small compared to the big numbers that I told you, but we need to grow. We used to build, even a year and a half ago, 1 box a month. Today we build 1 box a day. That's 30 times in about 16 to 18 months. And remember, the supply chain for the kind of things that we do, the people that make the parts don't exist. We are creating a supply chain. We're not just building a company, we're building an industry. It takes time. But we'll get there, and we are in a hurry. And you can see the environmental impact. So there is an example of what happened at Caltech. And this is interesting because when we announced the Bloom Electrons program, you can see the boxes sitting out there. Would you imagine if you had a 1 megawatt diesel generator out there producing electricity? People sitting out there and having a press conference and enjoying a good day? Okay? That's pretty remarkable. We can put it on rooftops, like what we have in Adobe. It's about a 1.3 megawatt installation. Or we can put it on a lawn as a showpiece. That is that's the PayPal building of eBay. It's their headquarters building. So we made it architecturally from an industrial design perspective. Make it look attractive. So it's not the old generation, your father's power plant. It is something that you can have outside your bedroom window, you can have in your lawn, and show your employees, motivate your employees that you're being nice to the planet. How would you do that if you painted industrial green and put vents all over and a little chimney coming out, right? Nobody would want that in their backyard. So we had to think through that process and say industrial design is very important. Make it look attractive. Make it look something that people can be proud of. And it doesn't make noise. It doesn't emit stuff. I always keep getting asked the question, but you live on subsidies, you need subsidies. Is your cost going to come down? Where are you going to be? I want to put this chart up. Any new technology that you do, if you're going to get into it, you need the equivalent of a Moore's law. You all know Moore's law from computing and what it means to the semiconductor industry. You need something like that. It's going to be a different law, but you need something like that. So look at this number. When we shipped our first unit to Google, that's not what we charged them, but it costs us 35 cents a kilowatt hour. Again, I don't talk about the box. The cost of the box does not matter. The product coming out of that is electricity. You all pay for electricity. You pay a certain rate, right? That's what matters. That's what you got to compare against. Then it's apples to apples comparison. And within 10 megawatts, within a year and a half, 10 megawatts is 100 boxes. So imagine you build the Model T car factory, and the 100th car coming out is half the price of the first car. And you didn't have volume to help you. 100 is not a number, right? 100 can barely do this side of the campus. So in something that small. So my question to you would be, look at this and ask yourself why you can't do this and this. I know what those numbers are, but in Bloom, we never talk about anything until we do it. We've done this. I'm not going to tell you what these numbers are going to be. But I just want to leave you with a very profound saying on this particular chart from Edison. Edison said, I'm going to make light bulbs so cheap that only the rich can burn candles. Okay? I'm going to make electricity so cheap that only the rich can burn coal. that's when green takes off. If we don't do that, we can't expect the world to embrace sustainability. It has to be affordable and sustainable. It's an issue of and not or. So I talked about the input flexibility. Let me just focus a little bit on the output flexibility. We can do AC power, DC power, things like that. So again, I'm going to bring on Edison to think about. You know what? Edison was right. He was just ahead of his time. For those of you in electrical engineering and power engineering and who know history, there was this big thing between Tesla and Westinghouse and Edison, and whether it's going to be AC or DC. You know what? Edison was right. He was just ahead of his time. So think about a data center. I thought this is a good example to use out here. What happens in a data center? Every single server runs on DC. You have an AC to DC converter. In each server, it costs about 60 to 80 bucks today. It loses 15% of the electricity right there in that AC to DC conversion, roughly, on average. Some are a little more efficient, some are a lot less efficient. Okay? So what happens to that 15 to 18% that gets lost inside the data center? It becomes heat. And what do you do in a data center? You need to cool. So you put a huge HVAC equipment to do the air conditioning, and you put more electricity into that box to remove that heat. We can natively produce DC and do this. Not only is our box a lot more efficient, but look at what you can do on the downstream side. But then take this a little farther and think about the future. What are the things we all use electricity for at home? Lighting. LEDs are going to rule. Okay? What does LED lighting take? AC or DC? DC. What does your cell phone, your laptop, your big screen TV, what do they all take? DC. Why would your heat pump, air conditioning, and refrigerator not run on a DC motor? The home's going to be DC. Okay? Businesses, significant number of businesses are going to be DC. Wherever the grid is, the grid will live in parallel with what we have. I'm not saying it's the end of the grid. The mainframe never went away. The mainframe is called a data center. It's made of multiple servers. Okay? That are small. That's exactly what will happen in this industry. And it'll take many forms, and one size will not fit all. What works in a remote village in Africa will not be the same solution for what happens in New York. What you can do in Arizona with all the sun will not apply in London. So there is no one solution, like I said. And again, sorry for using the Bloom example, but I just used it more to inspire the thinking that went behind it. These things didn't happen by accident. You need to have thought through many of these things even before you start designing, building a product, building a team. And if there's one message I want to leave you, it's that the world of opportunity as we see going forward for us to make a contribution to society is going to be extremely interdisciplinary. And you need to think very differently about it. And you need to understand business. You need to understand why something will succeed, not succeed. And that often involves a lot more than technology. So with that, I'll just stop, and if there is time, I'll take questions. Dean?
Sure, that's fine.
Thank you.
How does the Bloom box respond to change in demand? So, we have peaker plants today that have to be brought online with natural gas to handle surge in energy use during a hot day.
Very good question. So the question, if any of you in the back didn't hear it, is how does the Bloom box load follow when power needs go up or go down? Again, a very prudent approach that we took, similar to what we did with the fuel. We started with natural gas, use it as a bridge fuel, and then bring in other fuels. Similarly, on the output side, what we said was we will start with base load that stays flat. And then our second iteration, third iteration products will do the load following. So that's what we've done. Is it capable of load following? Absolutely. Do we have designs that we're working on towards that? Yes. Does it exist in the product that's out there? No.
And some of the challenges to financing distributed generation projects is they're too small for the major banking institutions to be interested without creating a portfolio of projects. How have you guys overcome that to get Credit Suisse, for example, interested in participating in this? Do you inventory those projects yourself and hold them on your balance sheet, or do they take that and do the inventory for you?
It's off balance sheet, but it's a project company that we have, and the financial institutions line up at the doorstep wanting to do this. So if you have the right value proposition, money in this field is not an issue. Okay, and I can't say the exact numbers, since we're a private company, but I can tell you a few $100 million have gone into Bloom as an investment to take us to where we are. And at no stage in our 10 years have we ever had any problems finding the right investors, which means we chose who we want to pick. So build the right value proposition, have the right product, have the right team, investors will come.
Nowadays, a big concern is for the pollution caused by cars. Are there any plans in Bloom Energy to produce some sort of generator that could power electric cars using natural gas?
Very good question. So you are actually touching upon something I left out when I talked about AC versus DC. Till even last night, I drove the only plug-in hybrid Prius that's in the U.S. today. They gave it to us for the first month when they brought it to the U.S., the first car. And that will be a very big play very soon, plug-in hybrids from many different companies. And you can look at Tesla and others and what they've done, and other electric cars will come. So if I were to take Tesla as an example, if you use 110 volts and try to charge that battery system, it'll take you about 16 hours to do a full charge, between 12 and 16 hours to do a full charge. If you have a 210 volts, it'll take you about 8 hours. Bloom produces natively a 400 volt DC, and we provide that as an outlet. It'll take 30 minutes to charge the car. So forget the fact that you're losing all that AC-DC conversion and all that for the battery. The ability to at least half charge your car in 15 minutes while you're grabbing a cup of coffee or a burger and to be able to go is just a phenomenal value proposition for a customer. So Bloom, at least for the foreseeable future, we don't want to be in your car, we want to be your gas station. Yeah?
What is the byproduct of burning the hydrocarbon to electricity?
So, very good question. What is the byproduct? How does it compare? So what happens when we take natural gas? I'll just use that as an example. Natural gas, you all smell something when you have natural gas. Those are mercaptans that are just put in there to make it noxious so you will know when there's a gas leak. Okay? That's sulfur. When you burn it in a combined cycle, a gas turbine plant, that SO2 comes out and you process it later on. What we do at Bloom is we desulfurize the fuel before we send it to the fuel cell. So we desulfurize the fuel before we send it to the fuel cell. So all the sulfur is trapped. There's absolutely no sulfur coming out, number one. Only oxygen goes across the fuel cell, which means where the reaction is occurring, there is no nitrogen. So there is no NOx. It's all oxygen combining with that, so there are no particulates. Okay? So we don't have particulates, we don't have NOx, we don't have SOx. Because it's a hydrocarbon, C and an H, you will get CO2 and water. Those are the only two things that come out. If you stand next to it, you will not smell exhaust. You will not see a plume, you will not see, you'll not smell an exhaust. It's got CO2. But because of the high efficiency and the lack of transmission distribution compared to the marginal rate of what we need to do, I showed you the efficiencies. We put out a lot less CO2 for the same amount of electricity produced. There are eBay's campus that I showed you, the PayPal, uses landfill gas, the methane from the landfill gas, to power that. There, we are carbon negative, because if somebody didn't have a market and buy that methane, it would go into the atmosphere. Methane is an order of magnitude greater in global warming contribution than CO2. So for every methane molecule that is brought into the plant, one CO2 comes out. So eBay, as it's using electricity, is carbon negative from that account.
So you said that the Caltech campus was running off 1/3 of Bloom Energy servers. Has a similar proposition been spoken over with our faculty and our administration?
There are two things, and this is the reality of where things are, and it's a harsh reality. The harsh reality is the following. Cost of electricity in Illinois is a lot cheaper than cost of electricity in California. A lot of Illinois' electricity comes from coal. At this current point, till we take a couple more steps in that Moore's law, we can't compete with that cost. And since we make very few, so if Illinois were to buy it, it needs to be a different value proposition and not the bottom line value proposition. Okay, that's one. The second thing is the state of California has very good incentives right now that make it attractive. The state of Illinois does not, and I don't think, given your budget situation, they'll create one. I would rather it go into your R&D and tuition than come to me.
More questions?
You were talking about. Yeah, you were saying that your customers buy electricity from you at a reduced unit price. So is there like a conflict of interest between your company and the government in terms of them not able to sell the electricity to the company?
Oh,
or as a follow-up to that question, how do you see your product penetrating the rural market, considering government? I mean, you need to replace the government grids and things like that there.
So the question is about, are we competing against the government? And thank God, no. Electricity more and more, what you're talking about is a while ago. Electricity more and more is a deregulated entity. In the US and even in other developing countries today, more and more you will find that electricity is a private enterprise, but it's a regulated enterprise. They can't charge whatever they want. What happens in the US is every state has something called the PUC, the Public Utilities Commission. They regulate the price, but Illinois Power or whatever you have, that's not a government entity. That's a private entity. Okay? So we're not competing. And again, even with the utilities, we're not competing. And that's an important point, and let me just elaborate that in 30 seconds. What I mean by that is, it depends on what a utility would like to define itself as. If a utility wants to define itself as the company that owns poles and wires and wants to gouge you, then we compete with them. If a utility says, I'm in the business of selling my customer electricity and giving them a good value proposition and making a profit in the process of doing that, then we are their friend. Because the utility can buy the box, the utility does not make the power plant. Okay, they don't design it. They just run, operate, maintain. There's no reason why they can't run, operate, and maintain Bloom boxes and serve it to you with all the attributes and collect the money. So it's not a conflict.
One of the things with fuel cell development is precious materials that are used for catalysts and things. That's been a huge issue in terms of getting it into the market because fuel cells have been here for so long. You're right now at a stage of building several tens of thousands, and then you're highlighting the problem of 4 billion people. How do you see this materials issue interfering with how your technology scales in the future?
You know, there is always a threshold point. And yes, you're right. We are acutely aware of the history of fuel cells because one of my co-founders in the early 60s built the very first fuel cell that flew in space for the Gemini spacecraft, which was prior to Apollo. That's where the first fuel cell flew. So we are acutely aware of the 50 years of people trying. But similar to what happened with flight, if you take flight, right? Several people over several centuries tried to do flight, and finally somebody cracked the code. So we would like to believe that we are the ones that are going to crack the code. And that's an entrepreneur for you. I'm an optimist. I don't see a cup as half full. I see it as overflowing. I'm a guy of abundance. Okay?
How long does a bloom box last, and what are typical things that break down?
Very good question, or questions. We warranty and guarantee the performance, efficiency, and output to our customers for either 10 years, 15 years, or 20 years, okay, depending on what they sign up to and how we maintain it. And during that time, what has to get changed? The stacks have to get changed every once in a while. The fuel cell stacks, the bread loaves that I told you. So what happens inside that bread loaf? It's the fuel cell. They are catalytic material. The catalytic material will structurally change because of the high temperature and the reactions that are going on, and it'll drop in efficiency. But they don't die, and you'll be surprised with what we do. When we get to 45% efficiency, lower heating value to AC power, when we get to 45% efficiency, we say that that fuel cell does not work anymore, and we replace it. Most power plants will be happy to start their life at 45% efficiency, okay? Because it's our belief that the price of fuel will only go up with time. I'm not talking about the spot market that can go up and down, but you saw the problem of supply-demand. So higher and higher efficiency is the better way to do it, and there's a value proposition. The good news is, because we planned it that way, we can take those fuel cells, which are ceramics and other powders, simply crush them, reuse all the materials. It's completely recyclable. Okay? And as long as we keep bringing down the cost of making that, we can afford to do that. And we can afford to run at a high efficiency. So that's the value proposition. Okay? Good.
John?
So you've talked some about the growth of your company, and I just have to ask, why hasn't it grown a lot faster? What's preventing you from expanding even more?
You sound like me asking my employees that. It's one of the most frustrating things, without a question. As an entrepreneur, you have a sense of urgency, and this is about a mission. We know why it's important. We know what to do. But I think I answered it. Let me elaborate on that. We're not building a company. We're building an industry. If I'm building the next electronic gadget, okay, now I know who will design the chip. Once I design the chip, once I design the architecture, I know who will fab it. It'll be one of the big, semiconductor fabs. And I'll know who will take that chip and do a printed circuit board for me. I know who will package it for me, okay? I can go all over the world, right? Apple can do that. They have a great partner in Foxconn, right? Very easy to do. For what we do, we don't have the equivalent for a lot of those things because it's a brand new technology. There is a metal part out there that's a powder metallurgy part. It's a 1,600-ton press. There are 2 1,600-ton press makers in the world. You place an order, 13 months later, you'll get one press. Okay? We are changing all that, but I need to work with them to increase their capacity. I need to work with a powder metallurgy company to increase their capacity. And these are bricks and mortar, 4-story tall factories. And by the time they get permitted, built, everything, it takes time. And you can't place all those orders before you have proven out your first box. Okay? But when you place those orders, it takes time to build it. So it will take time. Anything of this nature, which is not bits and bytes, right, is going to take time. That's why I said this energy opportunity is an opportunity that you guys will be talking about when you have grown up as students. Okay, it's a great opportunity.
KR mentioned that Apple has Foxconn as a partner. Actually, the senior vice president of Foxconn should be somewhere in here. Is he here? Oh, stand up, stand up, stand up. Yeah? That's an alumnus, okay? That's Sidney Lewis here to receive a distinguished alumnus award from mechanical engineering. So we have the whole world covered, okay? It came from Taiwan. Two more questions. At the back. The tall guy at the back. You.
We can see that how your technology can make a difference in developing countries. So what steps are you taking in that direction?
By the time it gets, so almost all our installations so far have been California-centric. Why is that? One, the market opportunity is good at that high cost, number one. As you would imagine, I think you're from India, right? Yeah. Okay, so if you take India, they're extremely value conscious, right? At the end of the day, you need to make that value proposition to them. And India does not have subsidies. So can you enter right away? No. But can you enter in a couple of years with that Moore's law? Yes. So we will work on that. That's number one. Number two is, by the time you go international, global, you want the product to be extremely robust. Your early deployment needs to be very close to the engineering team, very close to the technology team, because things happen. The best of intentions, you can design whatever you want, but you need to learn on the field. You can't simulate everything you want to in your lab. So you need to learn that. So there are multiple reasons, but believe me, if Bloom becomes an extremely successful company financially and does not do the mission of changing the world, in my personal opinion, we would have failed. Because there is a thing that we have at Bloom. We talk about missionaries and mercenaries. We talk about success, and we talk about success and significance. To me, it's success and significance. I'm a capitalist. I would like to be successful, but I also want significance. It's not either or, it's and.
Thank you.
One more question. The guy in orange.
There'll be a lot of them.
I know in Illinois, the producers of renewable energies, they could sell back their excess energy to the grid. Is your system capable of that, and are your customers currently doing that in off-peak load times?
Yeah, our systems are capable of doing that. They are grid-tied, so we can net meter, we can take excess power from the grid if you want to give more, or we can do any of those things. But typically our customers buy it for their own needs, because our demand is significantly larger than our supply. We don't have to net meter. And again, if you put a solar at a home, you need to net meter unless you have big battery banks that do the storage, because in a home between day and night and everything else, your power usage is very, very different, and the sun shines only for a small amount of time. With our system, it's a 24/7, 365, always on baseload, and we produce electricity. Once the box is purchased, we produce electricity cheaper than the grid, so there's no reason why somebody will go buy from the grid. So we don't do that today, and we would rather be serving the customer than the utility.
Well, I know there are very many questions, but there'll be reception where you can ask KR more questions. I think it's 4:10, so let me present this to KR. This is a symbol that you've come here today. It's
Thank you.
This Distinguished Leadership Lecture on Energy by KR, and the University of Illinois is written very boldly on this.
Thank you very much. Thank you. Thank you.